Alrighty, night number 2. Night number 2. Curiosity strikes. Should we jump straight into it, or should we wait a little bit? Alright, so starting with this one here. So we've done all these questions so far, except for one of the questions on statistics, which I explained why. But let's continue on with this one now. Okay, not may as well, but we will finish this off and then we'll get some answers up. So do it in a moment. Just chill for now. Enjoy the music while it just gets prepared, which I should have done well in advance, but you know. Hope the music's not too loud. The in the other one it was really soft, so I turned it up a bit. And hopefully it's a bit better. Not better, but you know what I mean. Alrighty. Let's have a go. So first one, 22. Given a function f of x is equal to x squared minus 1, and g of x is equal to the square root of 4 minus x squared. Sketch y is equal to f of g of x over its natural domain. So f of g of x. So pretty straightforward this one, f of g of x. Okay. So the way I like to think of this is, well, if f of x is equal to x squared minus 1, and we did one of these last night, I'm pretty sure, or the night before, then f of g of x is the same as if I was to write f of the square root of 4 minus x squared, okay, and f 4 minus x squared, okay, is equal to, so every time we see an x in the original f of x, we're going to replace it with the square root of 4 minus x squared, so this is 4 minus x squared, all squared minus 1. So what does this function look like? Well, the square cancels with the square root, so we've got 4 minus x squared minus 1, so my function is going to look like, so f of g of x, or y in this case, is the function y, is going to look like 3 minus x squared, or minus x squared plus 3. Now, we need to look at what the natural domain is for this case, okay? So what numbers can I substitute into this value to make it work? Okay, so in other words, what numbers can I put into this guy here? Because that's the numbers that are effectively going to tell me if this thing's going to work or not. So 4 minus x squared, so this is for the domain. It's going to be greater than 0, or equal to 0 in fact, because it could be 0, because essentially any number that's 0 or bigger than 0 will work in a square root. Okay. So let's solve this. We get minus x squared is greater than or equal to negative 4, which means that x squared is less than or equal to positive 4. Because the positive 4, when you multiply by a negative, okay, in an inequality, it swaps the sign around. Okay. So we're going to either have our values being between 2 and negative 2, or outside of 2 and negative 2. So let's try a point. So let's try x is equal to 0, So x squared is less than 4, so 0 squared is less than 4, which is true. So then my domain is going to be that the x value is going to be between -2 and 2. Okay. Now it is a parabola. Okay, so it's 3 minus x squared between -2 and 2. So 1, 2, -1, -2. It's not going to go outside either of those. Okay, now the parabola 3 minus x squared, or the y-intercept, is 3. Okay, so it's my y-intercept. Okay, and it's just a regular negative parabola. So 1 across, 1 down, and then 1 across, and then 1, 2, 3 down. 1 across, 1 down, and then 2 across and 4 down, if you will, or another 1 across and 3 down. So the function should look like this. Something like that. And we can, well, it's not actually going to have arrows on this one, because we know it's going to stop at, it's going to stop at 2, because remember it's in its natural domain, it stops there at 2. So what's that final value at 2, -2? Well, this is at -2, and substituting that in, we get -1. And down here we've got 2 and -1 here. And we don't particularly care too much about the x-intercepts in this one, because we've actually got bounds for this graph. And so that's basically it. So this is our graph of this parabola. Cool. Okay. Given the series tan squared x minus tan to the power of 4x plus tan to the power of 6x minus tan to the power of 8x plus ... for when x is between -pi on 2 and pi on 2. We're going to determine the values of x such that the series has a limiting sum. So we're looking for our limiting series in this one. So again, as I said, you've got your formula sheet. So we'll pull that up for this one, because it's going to be very useful, because our limiting sum for any sequence or series is on there. Okay. And the formula for our limiting sum, okay, is S is equal to A over 1 minus R, where R is less than 1. Okay. And because of this domain here, because of this domain, tan will be, or the value of tan is always going to be between between 0 and 1, or -1 and 1, I should say. Now, so for this value, we need an A term, so we need an A. Okay, and A is our term that we start off with, so that's pretty easy. That's tan squared x. And our R value. Now, our R value is the value that it's going up by each time. So it's swapping between negative and positive in each jump. So my R value is going to be negative something. And what's it going up by each time? Well, it's going up by tan to the power of 2. So we're multiplying it by tan squared. So each time we're jumping it up, we're multiplying by tan squared, and we can see that because, you know, when we do tan squared x times negative tan squared x, okay, when we multiply same bases, okay, we add the powers, so it's going to be tan to the 4x, okay, or negative tan to the 4x, and then when we do negative tan to the 4x times negative tan squared x, we're going to get positive tan to the 6x, okay, because we're multiplying, we're doing that as index laws for each jump. Okay, so from here, what we're going to do is we're going to work out what the limiting sum is going to be. I'll determine the values of x so that the limiting sum. So we're not up to the limiting sum just yet. So we've actually set up for the next part, but we're determining the values of x such the series has a limiting sum. So it's when x is between these two guys here, okay? But our first value, if you have a look at it, it's tan squared x, or it's negative tan squared x, okay, is our jump that we're going through each time. Okay, and this is what our r value is. So our r value is negative tan squared x. But we also know from this guy over here, the absolute value of r has to be less than 1. So what this implies is that negative tan squared x, okay, the absolute value of that, because that's what r is, has to be less than 1, okay? And then we'll essentially solving this, okay? We know that if x was between negative pi on 2 and pi on 2, then when we solve it for tan squared x, okay, so it's tan squared x, we would get that. Now let me just think about this for a sec. I believe it's negative pi on 4 and pi on 4, because, yeah. So the absolute value of this is less than 1. Okay, so for what values of tan squared x are less than 1? Okay. So in other words, it's when x is, so our, my inequality is this for my x value, but I'm looking for tan squared, so I need to essentially square both sides. That doesn't sound right. Let me think. It's actually quite a tricky one. So negative tan squared x is less than 1, so it's between minus. Well, when we solve an inequality like this, any quadratic inequality or any inequality, you've got two solutions. You've got when tan squared x is equal to 1, and when tan squared x is, is when it's equal to, when it's less than 1, and then it's greater than negative 1, okay, because we multiply both sides by negative 1. Because if this guy is equal to negative 1 on the inside, okay, the absolute value of that is going to be equal to 1 as well. And so we're looking for when it's less than that, okay? So we've got two equations which we can solve, okay, from this point. So when is tan squared x equal to 1? Well, tan x is equal to 1 when x is equal to pi on 2. So tan squared x would be equal to 1 when x is equal to pi on 4. So it's the square root, I guess you would say, or the yeah. So, and just swapping that inequality back in, so it's less than. So x is less than pi on 4, and then same thing this side. So when is tan squared x greater than negative 1? Well, if x is greater than, if tan x that's greater than negative 1, when x is greater than pi on 2, or negative pi on 2. So tan squared x is going to be greater than negative 1, when x is going to be greater than pi on 4. Okay. So, therefore, x is going to be between pi on 4 and, negative pi on 4, like that. Okay, so that's the values which make this limiting sum a thing. Like, so for example, if I put, say, pi on 3 into, any of these values here, we're going to get, well, if I let x be equal to pi on 3, then the number that we're multiplying by each time is actually going to be bigger. Then it's going to be bigger than the 1 value, which we want it to be less than. So the value where tan squared x is equal to 1 is pi on 4. So we want values where it's in between those, essentially. Okay, part 2 is now when we use the sum. So s is equal to, so it's going to be a on 1 minus r Our a value is tan squared x, and our r value is equal to negative tan squared x. Okay, so substituting that into the formula, we get s being equal to tan squared x on 1 plus tan squared x. Now, I don't know if you guys know this, but I'll just do this on the side here. There's a cool little trigonometric identity, and you may have seen this one before. Cos squared x plus sine squared x. What's this equal to? Okay. Hopefully you know that that's equal to 1. What happens if I divide everything by cos squared x? Okay, so divide that by cos squared x, divide that by cos squared x, and divide that by cos squared x. What happens? Well, that cancels out and we get 1. Sine divided by cos, well, that's tan, so tan squared x. And then 1 over cos squared x is sec squared x. And we get this new identity. 1 plus tan squared x equals sec squared x. So wherever I see a 1 plus tan squared x, I can actually replace it with sec squared x. And I hope you can see that I've got exactly that over here. So I can replace the 1 plus tan squared x with sec squared x, okay? And I'm going to run out of space here. You could jump straight to the answer if you know what the answer to this is going to be, but we know tan squared x is going to be sine squared x over cos squared x, okay? A fraction is just another way of writing divided by, and sec squared is 1 over cos squared x, okay? So dividing fractions, okay? Multiply tops, multiply bottoms, like that. And the cos squared and the cos squared is going to cancel out, and we're actually just left with sine squared x, and in fact that's our answer. So the limiting sum, so if you keep adding, if you start with tan squared x and you keep multiplying it by negative tan squared x, you're eventually going to get to sine squared x, which seems really crazy, but there you go, that's the working out for it. So yeah, pretty cool, I think, anyway. But trigonometry, man, it's tricky. Ooh, a bit of working out for this one. Solve 2 cos 3 theta is equal to negative 1 for 0 to theta, theta between 0 and pi. Okay. Okay, so let's start off by trying to solve this equation. So we've got 2 cos 3 theta is equal to negative 1. So cos 3 theta is equal to negative 1 on 2. Okay. So from this point, what I actually like to think to myself is, well, if cos 3 theta is equal to a negative 1/2, when is just cos theta equal to negative 1/2? Okay, so what values of cos theta is equal to negative 1/2? So let's draw one of these guys. All stations to central. Okay, well, cos is negative in the second quadrant and in the third quadrant. Okay, but for our domain between 0 and pi, we only want the value that's in the first 2 quadrants. So it's at the point where it's in the second quadrant. So we're looking at the second quadrant. Now, when is cosine equal to a half normally? So when's it normally equal to a half? Okay. Well, cosine is equal to a half at 60 degrees, or pi on 3. Okay. So what this means is that if cos theta is equal to a half, then theta would be equal to pi on 3, okay? And that's in this domain, okay? Because there is another solution, but not in this domain. Then cos theta is equal to negative a half, theta is going to be equal to, now, to work this one out, we do pi minus pi on 3, okay? Because we're going to go at the 180, and we're going to go back around to where that value is, okay? So pi minus pi on 3. So theta is going to be equal to, in this case, what's that? It's going to be 2 pi on 3. Okay. So one of our values is 2 pi on 3. Now this is only if it was equal to theta. Okay. So theta would be equal to 2 pi on 3. But the issue is, okay, That's only if we've got theta being between 0 and pi. That's only theta. But we've got 3 theta, okay? So, to get from this theta down to this, whatever this angle is, well, what do we have to do? What do we have to do to this theta to get it down to this one? Well, we've got to multiply it by 3. So we're going to multiply both sides by 3. So 0 times 3 is equal to, well, that's just 0. And pi times 3 is 3 pi. So our actual domain that we're looking at is from 0 to 3 pi. So it's not just from 0 to pi, but 0 to 3 pi. So we've got one of our solutions, okay, which is this one down here. Now we're going to look at our second solution. So when we've changed our domain, that's going to include this value down here. Okay, so theta could be in the pi plus pi on 3, which is equal to 4 pi on 3. And finally, we've got the other one. So, well, there's only 2 values where that is, but because it's 3 theta, we're probably presuming that there's going to be 3 values. And in fact, there are 3 different values. So let's take the next value, okay, and we'll test it. So we're going to go all the way around to where it's next equal to -1/2, which is 2 pi plus pi. So theta, 2 pi plus pi plus, minus pi on 3, okay? So these should give me all of the values it's going to be between 0 and pi when I go back around to it. So doing this last one, we get 3 pi, take away pi on 3, which is the same as 8 pi on 3. Okay, so finally, remember these are the values for 3 theta. So we're saying 3 theta, so this is 3 theta by the way, 3 theta, and what's some 3 theta? So these are all 3 theta. Okay, so 3 theta is equal to 2 pi on 3, 4 pi on 3, and 8 pi on 3. Okay, so it's equal to all these different values. Okay, because there's 3 possible solutions there could be. Okay, and if this is what 3 theta is equal to, but look at our original domain. Remember, we're trying to find what theta is, not what 3 theta is, what theta is. So finally, we're going to go through and divide everything by 3. And we're going to get 2 pi on 6, which is just pi on 3. We're going to get 4 pi on 6, which is just 2 pi on 3. And finally, we're going to get 8 pi on, sorry, not 6, on 9. Wow, I can't actually do division. Wow. Which aren't going to simplify, so 9, 9, and 9 like that. Okay. And so those are our 4 solutions. And you can check too, because each one of these 3 solutions is between 0 and pi, because 9 pi on pi, 9 pi on 9 is what pi is equal to, and each one of these is smaller than that, and obviously bigger than that too. So those are our 3 solutions that are going to make this. Now, if we added a 4th solution on, so we could try the 4th solution. So try this one, next one down here. So if we added on, if we added on 4 pi on 3 to 2 pi, we would have got so 2 pi, which is 6 pi on 3. So we've got 10 pi on 3. 10 pi on 3, which turns into 10 pi on 9, which is bigger than 9 pi on 9, so that one doesn't work. Okay, so essentially the amount of, the number on the inside, like the shortcut is, the trick is, the number on the inside here next to your theta is basically how many solutions you should have. Okay, because we had 3 theta, we should be expecting to have 3 solutions. Okay, expecting. It's not always going to be the case, but it's a quick trick to check. Like 9 times out of 10, you're gonna have those values. The only time it doesn't work is when you have your sine or your cosine equal to 1, so or -1. So those are the only 2 times when they don't work. Well, 4 times really. So if it's equal to 1, okay, there's only one place where it's equal to 1, and that's when it's straight up, when it's at pi on 2 degrees. Okay, so that one doesn't quite work. And coincidentally for cosine, it's only equal to 1 when it's at 0. So, there's no other point where it's going to be equal to that as well. So you would have to, you might not have as many solutions as what you would have for one like this. Okay, next one, let's have a look. Differentiate sine squared x. Okay, well, sine squared x, how do we deal with sine squared x? Well, let's have a look at the formula sheet and see what we've got on there. Now, on your formula sheet, it has a formula, funnily enough, that looks like this. It looks like sine squared nx is equal to a half, okay, a half, well actually we don't even need to do this, jeez. It's not even a formula, it's just a straightforward chain rule. So, sine squared x, so if we call this y, sine squared x is just the same as sine x all squared, right? Okay. So how do I differentiate this? Well, you bring power down the front, so y dash is equal to 2. Okay, the derivative of the inside comes on the outside, so cos x, and then sine x, and then you subtract 1 from power, so it's just 1. So that's it. It's just 2 cos x sine x. Like that's all you got to do. And for 1 mark, it should be pretty straightforward. Okay. Yeah, I was starting to do thing. So that's funny. Anyway, okay. Next question. Hence, calculate 0 to pi 4 of sine x plus cos x all squared dx. Leave your answer in exact form. Okay, so well, for this one, I think we're going to start off by expanding it. So 0 to pi on 4 of sine x plus cos x squared dx. Well, this is the same as from 0 to pi on 4. Okay, use your binomial expansion. Sine squared x, okay, plus cos squared x, okay, plus 2 lots of sine x cos x dx. Now, if you're not 100% sure how to do that one, what you could do is you could do sine x plus cos x, sine x plus cos x. You could expand it this way. So you do the first, outside, the inside, and the last. You use the FOIL method. Or the way I did it really quickly was I said, okay, well it's this squared plus 2 lots of the product of the two. Okay, that's the quick way to do it. So that's what it is. That sine squared, which is cos squared plus 2 lots of sine times cos. Okay. Now looking at this, I can see a trigonometric identity in here. Okay, and we talked about this one before. So if I go back up here, sine squared x plus cos squared x. So up here, cos, or the other way around, but cos squared x, sine squared x. If I zoom in, it's this one here. Cos squared x plus sine squared x is equal to 1. So we can actually replace this, and it makes this whole problem a lot easier. So we can replace what I've underlined there with 1. Okay, plus 2 sine x cos x dx. Okay. Now, well, actually, we don't need to do the integral for this next bit because we can actually integrate it now. Okay. So the integral of 1, well, that's just x. That's nice and easy. The integral of 2 sine x cos x. Well, this is where part 1 actually plays its role. So what we were asked to do up here is we were asked to differentiate sine squared x to get we were asked to differentiate sine squared x to get to cos x sine x. And when we integrate, we're doing the opposite of differentiation. So basically, I'm starting at this point and I'm moving back up to this one. Okay. So if we go back down and have a look, well, we've actually already got 2 sine x cos x in terms of, well, we've already got a 2 sine x cos x, not in terms of anything. We've got 2 sine x cos x already, but we already know what the we know what the primitive function of this is because we've worked it out. We've differentiated to get this solution, and in fact, it's equal to sine squared x. So what I can do is when I integrate 2 sine x cos x, well, that's just equal to sine squared x. Okay. And this is going from 0 to pi on 4. Now substituting our values in. Okay, so replacing x with pi on 4 plus sine squared pi on 4 minus 0 plus sine squared 0, okay? And we're leaving it in exact form, I believe. Yep. So, well, we need to know what the solution is going to be. Well, 0 plus, well, sine squared of 0, well, sine of 0. What's sine of 0 equal to? Well, it's just 0. So 0 squared is just 0, so this whole back end cancels out. So it disappears. Then we've got pi on 4 plus sine squared pi on 4. So sine squared pi on 4. So remember, this is the same as pi on 4 plus sine pi on 4 squared, like that, okay? So we've got the whole thing squared. So what is sine of pi on 4? Okay. Well, sine of pi on 4 is 1 on root 2. Okay, so go back to your reference sheet. It should be on there for you. So it's 1 on root 2, so it's going to be plus, okay, 1 on root 2, and then it's all squared like that, which is equal to pi on 4 plus, and then 1 squared is 1 over root 2 squared, which is just 2. And there's our answer. Okay, excuse me. A 6-sided die is biased, as shown in the probability distribution below. Find the expected value of x. Okay, expected value is easy, it's just another word for saying the mean, but a way we can calculate this one is quite simple. Okay, so the expected value of x is equal to, so all you're going to do is you're going to take the this value and you're going to multiply it by this one, and then you add it up, do the same thing, plus that times that, and so on. So it's going to be 1 times 0.1 plus 2 times 0.25 plus 3 times 0.05 plus 4 times 0.3 plus 5 times 0.17 plus 6 times 0.13, okay? And then we put this into our calculator, and I'm going to cheat because I could not be bothered to put that into a calculator because it's just a very straightforward sum. 3.5, well, sum and product, I guess. I guess it is a sum. But 3.58 is our solution for that one. Okay, so our next question, okay. Hence, using part 1, calculate the variance. Okay, variance is a little bit trickier, but we can do it. So there's 2 formulas that we can use for the variance. For this one, okay, I'm going to use this one. So it's going to be the variance of x being equal to e of x squared minus mu squared, okay? So all we've got to do is, instead of doing the expected value of just x, we're doing the expected value of x squared. And then once we work out, we just got to subtract the mean squared, that's it. Okay, now this formula I believe is on your formula sheet. In fact, if I have a quick look right now, yes, it is on your formula sheet. So this is one that's given to you, but what you need to know is how to use it. So how you use it is you do the expected value like we did before, but basically, so it's basically this whole thing here. So the ex squared is equal to all this, but all of the whole numbers, the x numbers, so these numbers in this top row, are all squared. So we get 1 squared times 0.1 plus 2 squared times 0.25 plus 3 squared times 0.05 and so on. I don't think you need me to read out these numbers. I'm sure you can see them. Okay, so once we've worked that out, all we've got to do is subtract the mean squared. So, or another word for the mean is the expected value. So that's why we need to do the expected value up here. So we could do this bit. So we're going to take away 3.58 squared, okay? And by doing this, we get an answer. So again, you just put this into your calculator. Very straightforward. We get 2.4636, okay? And that's all it is. So very, very straightforward question. It's just knowing what that table actually is. And getting the values, like understanding what the process is. But other than that, it's very straightforward. Okay. The body weights and metabolic rate recordings for 5 women are shown below. Okay, so as I said, I haven't actually done statistics, but that's alright because I can show you guys how to do part 1, and I can show you how to do part 2, and I'm pretty sure I can show you how to do part 3 as well. So, alright, let's do it. So we are going to be using the calculator for this one, and I'm going to make the calculator a little bit bigger just to, oops, I need you to come in front. Okay, so I'm going to make the calculator a bit bigger so you can see this. If that's big enough for you guys. So, here's my big trusty calculator. Let's have a look at how to do this one. So we're going to use the statistics mode for this one because it's the easiest way to do it. So we're going to hit shift. Sorry, we're going to hit mode and we're going to hit 2. Now we get a bunch of different gross stuff and we're going to hit number 1. Now, if your calculator just comes up with this, then that's not going to be very useful for us because we want a... No, we're not going to even hit that one. I told a lie. We're going to be hitting mode... we're going to hit mode 2, we're going to hit the number 2 because we want the X and the Y. Because our weight in this case is our dependent variable, our like our X variable, so 52, 63, 65, 47, 49. And the metabolic rate is our dependent variable, so it depends on what happens with the X, or we're presuming it does anyway. So now we're going to substitute our values in, so 52, we'll substitute, we're going to put them in, type them in. 63, 65, 47, and 49. Okay, and make sure you line these up. So 1671 equals 1669 equals 1812 equals 1442 equals and 1607 equals. Okay. Now we've done all this really hard work, so we're going to get rid of it because we hate it. I hate stats, going to get rid of it. I hope you liked my little joke because we haven't actually gotten rid of it. What your calculator will do is it'll actually store it in its memory, and if you don't believe me, if you hit shift then 1 and then you hit number 2, it'll actually bring your data back up. So it is still sitting there in its memory. So we're going to hit shift and we are going to hit that 1, and what we're going to do is we're going to do a little bit of statistical inference in the menu number 5. Now, in menu number 5, we've got 3 different buttons that we're going to be looking at mainly. We're going to be looking at this number 1, this number 2, and this number 3. Now, conveniently for us, the correlation coefficient R matches the value on the calculator. So if we hit 3, it's going to give us the correlation coefficient, which for some reason is wrong in the answers that I've got. That is very odd. I'm going to double check and see if I've put the scores in correctly, because if I haven't, then that would be very silly of me. 52, 1671, 63, 1669, 65, 1812, 47, 14, oh, there you go. Always helps to make sure that you've actually inserted your data correctly, because if you haven't, then we might get some mistakes. So let's try this again. So we're going to go 5 and we're going to go 3 and we're going to get a correlation coefficient of 0.82334011 blah blah blah, we don't care, but we're going to round to 3 decimal places, which is 0.823. Okay, and this is our R value, this is our correlation coefficient. So if you don't know what a correlation coefficient is, it's basically how close together our scores are. So this is a set of bivariate data, so it's like points on a scatter plot. And our correlation coefficient is telling us how close to a straight line is it making. So in this case, it is a positive straight line, so a positive gradient straight line. Now, the closer to 1, the closer together the numbers are. So 0.8 is pretty close. The numbers range between -1 and 1, so obviously -1 being not super weak, like so not spread out everywhere, but a very strong in the negative direction. A 0 R value would mean that there is no correlation whatsoever. Okay, find the coefficients of the linear regression line. Y is equal to mx plus c, where x is the weight and y is the metabolic rate. God, I'll get that right eventually. So, we need to know what these values are. So we need an m and we need a c. And again, we're just going to get these from the calculator. So if we hit shift and we hit 1, we go back to this 5 menu. Now we've got our two options, A and B. Let's start off by hitting A. Now A gives us 903, and this 903 is our constant term. It's the value that, I think 3 decimal places usually only once, so let's go 4, 9. So our C value, our constant value, is basically where our graph is going to start, where this straight line, the line of best fit, would it be on our regression line or on our scatter plot. It would start at 903.5 essentially. And of course that means that when we go back to the stat menu, we go to number 5, when we click number 2 and we hit equals, this 13.346 is our gradient. So for every one it goes across to the right, it's going up by about 13.346. Okay, so we found the m and c, and that's all we got to do. It just says find the coefficients. Okay, it doesn't say create the equation, it just says find the coefficients. If we were to create the equation, it would be y is equal to 13.346 x plus 903.499. And what this means is that you could use this equation to get an estimation about where your data sits in, or whether or not your data sits in a what's what I'm looking for, in a, oh my god, it's 11:45 already. Whether or not your data point would match the data set, or whereabouts it would fit if it was related, I guess you'd say. Okay, verify that m is equal to r times sy over sx, where sx and sy are the standard deviations of x and y respectively. So we need to start off by looking for our sy and our sx, and we're going to use our calculator to do that. So we already know what our r is, but we need to do our sr and sx, okay? So there's two ways we could do this. First way is to actually work out the numbers r and substitute them in. So to get to the sr and sx, shift 1, and we're going to hit 4 for variance this time. And as you can see, we've got our sx and our sy here. So we'll start off with our sx. We get 8.258. Yep. 8.258. So that's sx, and our sy is going to be shift 1, 4, and 7 sy. So it's going to be 133.864. Remember, the standard deviation just means how spread out your numbers are. So this one is quite spread out. Now, we know what our r value is. So the first way I said is we could actually substitute these values in and see if it works. So we should end up with our gradient, so 0.823. So sub these in, and we get m is equal to 0.823 times, remember because there's a times in between these two. It's going to be 133.864 over 0.823. Okay. So 0.823 times, or it's in stat mode, so it's going to be gross, 133.864. Now, if you don't like this fraction here, you can go back to the composite mode by pressing mode then 1, and it'll put your calculator back in the mode that you need, but I will bear with it for now. Put that in, we get 133.3. Okay, well, it's going to be a little bit off. It's going to be quite a bit off. Why is it quite a bit off? If I use the wrong standard deviation, was I meant to use the population? So I reckon the answer, well, it should be like 13, and I've got 133, which is huge. Have I used the wrong number? Yes, I used the wrong last number. Okay, that makes sense. Because that number's the same as that number. Okay, duh. So it's not 0.823, it's the other 8.258. So 8.258. I'm gonna get something that's close. So there you go, like 13.341. So it's pretty close to the m that we've got up here. Like very close, in fact. It's only 0.005 away from it. So really close. Now, if you don't want to do all that calculations, you could just use your calculator to do it. Actually, in fact, for this question, you'd have to do that to verify it. So you'd have to put the numbers in and then work it out to show it. But you can put these straight into your calculator. So if you hit Shift, Stat, and you go 4. Sorry, we're going to go 5 first, aren't we? So we're going to go 5, 3 times Shift Stat 4, and it's the SY on top. So 7 over Shift Stat 5, 4 and 4 again, okay? And it gives you the number that we just got. In fact, it actually gives you a number that's closer because it hasn't had to round like we did. So, much better way of doing that. But you would need to show your working out anyway. So this way is a no-no for your test unless it just said find the value of m is equal to r times sy and sx. So if you know what that was equal to, you do it that way. Cool. All right. How much more do we have to go? Because it's starting to get late here, and I'm getting sleepy, and I need to make more lessons. Well, we're actually almost done, so we might try and knock this over, I reckon. And then we can add up the 2 times and see how it went. But remember, it took me like 45 minutes to do multiple choice, which was crazy. It's a long time. It's much shorter to do this because I have to talk about the answers, I guess. Okay. Over to domain A to B. Okay, so here's A, here's B. Function f satisfies the following conditions. F of x is less than -1, and the derivative of x is less than 0, and the second derivative of x is greater than 0. Sketch a possible solution for this graph. Okay, so it's less than -1. Okay, so that means that whatever the function is, it has to be underneath this line. Okay, so it has to be under that line. The derivative is less than 0, so it has to be a decreasing function. It has to be going down. So decreasing. And when the second derivative is greater than 0, it has to be concave up. So an interval between those two that does that could be something that goes like, maybe like this, something like that. So that's a function that does that because it goes. So it's decreasing, it's going down, it's going down, it's going down. Okay, so if I drew a tangent, it's going in the downwards direction, but it's also concave up. Okay, because the cave is facing up. So that's my function. Okay. And it has to be between A and B as well. So you can't go past A and B for this question because it's telling you what the domain is. So yeah. That's really easy actually, that question. Write an expression for the minimum value of the function g of x is equal to 1 minus f of x. The minimum function. So what's the smallest function, the smallest value could be? Over the domain A to B. Okay, well, g of x minimum is going to be what? F of x's maximum. So the maximum f of x can be is -1. So 1 take away -1. Well, it depends on what the value of f of x is. Oh, well, okay. Think of it like this. The biggest value that my function can be has to be this value at a here. Because this function is always decreasing, it's always going down, the further left you go, the higher the values are. So the further I go back this way, the higher the values are. So the biggest value I have is the value that's actually sitting on at A. So what this actually means is that f of A is the maximum value of f of x. Hence g of x is going to be equal to, so the minimum, hence minimum for g of x is, and it's got to be g of a, because you've got to substitute a into it, and it's 1 minus f of a, like that. That's pretty straightforward, because it's whatever that value is at a, because it has to be the highest value. Cool. Alright, I'm happy with that. Okay, particle is moving along the x-axis. Its displacement x meters from the origin after t seconds is given by x is equal to e to the t minus 3e to the power of 2t for t is greater than or equal to 0. Explain why the particle never comes to rest. So, why it never comes to rest? The particle never comes to rest. So what does it mean when it never comes to rest? Well, it means that the velocity can never be equal to 0. Which means that the velocity is going to be constant. It's going to be a constant value. It's not going to be a value that's going to change. It's going to be a constant value. Or not 0. So it's either going to be constant or not 0. Okay, because I'm looking at the exponentials, and the exponentials tell me, well, it's not going to be 0. So, okay, let's work with this. So we've got x is equal to e squared minus 3e to the 2t. Velocity, which is just equal to x dot, which is equal to the derivative of the above, which is equal to dt of x, which is equal to, so it's going to be, well, derivative of t. So differentiating exponentials. Okay, if you have this, then it's going to turn into f dash of x e to the f of x, like that, okay? So this is like pretty much the golden rule. If you've got any function that has a function on the inside of it, so like an exponential, a logarithm, like a power or a trigonometric thing, you'll have to like take the derivative of the inside out somewhere. In this case, with the exponential, it's out the front. So e to the power of t is just 1, so 1 et, so it's just et, minus, and it's going to be, so the derivative of 2t is 2, so it's going to be 2 times 3, which is 6, e, and it's just the leftover again. So this is my velocity. So velocity is equal to, now if I just what's the word I'm looking for? If I factorize it. If I factorize it, I get 1 minus 6 e squared. Okay. Now, well, not e squared, because you're multiplying it. It's going to be e. If you're adding it, so e squared times e squared is e2 squared. Okay. So can this thing ever be equal to 0? Well, unit c cannot be equal to 0, okay, has no value of t. Makes e to the t equal to 0. Or you can't have ln of 0 be equal to t, because ln of 0 is not possible. Okay, and the other side we've got, so in this bit here, we've got, so 1 minus 6et is equal to 0, which means minus 6et is equal to negative 1, which means that et is equal to 1 on 6. And again, same as before. Well, it's not the same as before. Well, we can actually solve this one. This one's not equal to 0 or negative, so solve it like a logarithm. So take the natural log of both sides. t is equal to ln of 1/6, which means that t is equal to, so substitute, put it into your calculator, ln of, it's back into composite mode actually, ln of 1/6 gives us negative 1.79. Now, the issue with this answer is that we're dealing with time, and t has to be greater than or equal to 0 because it's time. Because it is time. Yeah, like it's time. Like you can't have 0 time, or less than 0 time. So, therefore, there are no values of t for which v is equal to 0, because the only value of t for which it is when t is negative. So there are no I should write this off, t greater than or equal to 0 for which v is equal to 0. Okay. That makes sense if you think about it, because like you can't have, I just realised my calculator is still in the big node. Like that makes sense if you think about it, because like you can't have negative time and the exponentials are never equal to 0 when you have an unknown in the top equaling to 0. So that's pretty much it. Okay, done. Easy. Right. Given the function, that's determine the coordinates of any stationary points and their nature. So stationary points occur when f dash x is equal to 0. So f dash of x is equal to negative 3x squared plus 18x minus 24. Okay, we can take a factor of negative 3 out. We get x squared minus 6x plus 8, I want to say. Okay, and then factorizing that, we get minus 3 is equal to x. It's going to be plus, no it's not, it's going to be minus 4. Minus 2. So therefore it's going to be when x is equal to 4, x is equal to 2. Now we're asked for stationary points. So y at x is equal to 4, y is going to be equal to something gross. Let's work it out. So when x is equal to, oh, it's just 0, isn't it? No, we're substituting this into your regular equation. So minus, because we're looking for the points on the graph. So remember, this is the derivative. Okay, this is telling us what the gradient's doing at those points. Whereas if we're looking for where the point occurs, we want to substitute it back into this for where the point occurs. Okay, so let's substitute it into that and see what we get. So we get minus on the outside, so minus 4 cubed, plus 9 lots of 4 squared, minus 24 lots of 4 plus 16. Oh, that's dumb. Y is equal to 0. And for the other side, y is equal to, so substituting 2 in. Should put this in brackets so I know that's what I was dealing with, but that's okay. So 2, I like putting brackets in like this because then I know exactly what I need to replace in my function. And that's it, and we get negative 4 for that one. So therefore, stationary points occur at 4, 0, and 2, negative 4. Okay. Now we need to determine the nature, so we're looking, so the nature, we're looking for the second derivative. Okay, so the second derivative of x. Okay, let's go back up to the first derivative, the very first derivative. Minus 6x plus 18. Okay, let's substitute our points in and see what they're doing. So at 4, it's equal to minus 6 lots of 4 plus 18 equals negative 6. So therefore, because it is less than 0, it is concave down, so therefore it's a maximum. And f of 2 is our last one. Substitute 2 in and we get positive 6. Yep. So therefore it is a minimum because it's concave up. So therefore, stationary points are 4, 0, which is a maximum turning point. Is it a maximum turning point? It's a stationary point that's concave up. So because it's not horizontal, so it is a maximum turning point. And we've got 4, which is a minimum turning point. I hope it doesn't ask us to sketch this because I hate sketching these things. Oh, for God's sakes. Labeling the stationary points and intercepts with the coordinates axis, sketch the graph of y is equal to f of x over the domain 0 to 6. Kill me now. Alright, so stationary points, we know where these are. Our stationary points occur at 4, 0. So here's one stationary point, 2 and negative 4. Is that right? 2 and negative 4? Yeah. 1, 2, 3, 4, 5. Make it negative. Make it rain, boys. 4, 5, 6. What do we say? Negative 4. So it's down here. Now, what type of point did we have at 4? 4 was a maximum, so it's going to look something like this. This one's going to look something like this. Okay. Do we know where our... Oh, it's at 16. Of course it's at 16. Whoops. So ignore all that. We're going to rejig this. We're going to go up by 4, 8, 12, 16, 20, 24. Wow. 8 minus 12 minus 16 minus 20. Okay. Yeah, definitely not much beats maths at midnight, that's for sure. Alright, so, let's put in this one. We're almost done. I think we're only up to 30 out of like 37 or something, so we're getting close. I'm definitely going to get this done by the end of tonight. That's my goal. Anyway, so let's, substitute these points in again. So we've got 4 zeros, so that's that point there. We've got the point 2, negative 4, which is down here. And we've got a y-intercept at 16, so that's going to be up here. Okay, so we know that this is a maximum here, so it's going to come down like that, and it's going to come down like that. We know this is a minimum, so when it comes down to this, there's going to be some form of swap over here, so it comes down and then back up, like, not like that. So it comes down, and back up, and it's going to come back up, and I'm presuming that the x-intercept is going to be at 1. Oh, I don't want to find it. I really, really don't. No, what? We're not going to find it. We're just going to pretend it's 1. Yeah, to say it's 1. We're going to pretend it's 1. How would you find that though? Literally don't know. Substitute 1 into it and see if it works. If you get 0, then it goes through there. So what's this? 1. Substitute 1, you'll get 0, and then you know that that's the x-intercept. So local maximum. Minus 24, so 6, plus, I think it was like 16. Yeah, plus 16, and you get that being equal to, what did we say? Negative 20. So the negative is a single number, not a point. Why is it not a point? This makes sense. Okay, 31 we're going to ignore because, as I said the other night, I haven't actually done a normal distribution yet, so we're going to just leave that one. We'll come back to that at some later point. And it'll also get me to bed sooner, so it's always good. Okay, the diagram below shows a rectangular prism, or a rectangular piece of metal that has been bent to form a gutter for the flow of water. The cross section of the gutter is a trapezium. Okay, you can see that's showed the cross-sectional area a of theta as a function of theta is given by a theta is equal to 100 sine theta. What's a 1 plus cos theta? Lordy lordy. Alright. So. Well, it's an area of a trapezium, so let's work out the area of the trapezium. So we're looking for the cross-sectional area. So it's h onto a plus b. So we know that this area length here is our a length. This is our b length along here. And this is our height in the middle. So what we need to do is we need to work out what this is, and we need to work out what this is. And we know they're going to be the same because we know that this angle is the same, and we know that this length here is the same. And we can make a right angle triangle like that, which means that they're similar. So we can work out what this length and this length is going to be. So let's call that x. So to find x, I believe it's the exact form, I believe. So we want it in terms of theta. So the exact form of theta is going to be... Oh. Well, this is 10 in here as well, isn't it? And this is also theta up here, because it is a triangle. Yeah, I'm happy with that. Alternate angles? Yeah. And the Z guys, that guy and that guy make alternate angles, they're the same. On parallel lines, that is. So... And we've got 10 in here as well. Yeah, so let's work out x. I'm going to do x over here, so it's going to be what? Tan theta. There's sine and cosines in this, so I don't know if I like this. Oh no, it's not 10 along there. The length is 10, isn't it? It's the diagonal. Duh. That's why there's no tans. So the hypotenuse is 10, and we want the opposite, so it's going to be sine. So it's going to be sine theta is equal to the opposite, which is h in this case over 10. So my h value is equal to 10 sine theta, and my x value. So x value, let's go this way. It's going to be cosine, isn't it? So it's going to be cos theta. So x over, and then we're going to be adding that onto 10, or 2 lots of those onto 10. X over 10. Excuse me. So my area is equal to, so the height is, so it's 10 sine theta onto a plus b, so it's going to be 10 plus it's 10 plus, like, so this is the top bit, so this is B. 10 plus 2 lots of 10 cos theta. Okay, because that's equal to 10 cos theta. And so is that. And then this bit in here is just equal to 10. So adding it all up, it's 10, and then 2 lots of 10 cos theta. So you get 5 sine theta. 10 plus 10, 20, isn't it? 20 plus 20 cos theta, like this. And then we take a factor of 20 out to get 100. So if we take the factor of 20 out, so we get 20 times 5 sine theta, which is 1 plus cos theta, which is 100 sine theta, 1 plus cos theta, as required. There you go. Alright, find the angle theta that maximizes the cross-sectional area. Well, that's when a theta is going to be equal to 0? No. The derivative is going to be a stationary point, so it's going to be equal to 0. So whenever you're looking for a maximization or a minimization, you're looking for a stationary point. So we're going to have derivative equal 0. So let's expand our thing out. So we've got a theta. That's going to be equal to 100 sine theta. Do I want to expand that? No, I think I'm going to do product rule. So u is equal to 100 sine theta. U dash is equal to 100 cos theta. V is equal to 1 plus cos theta. And V dash is equal to negative sine theta. So V U dash plus U V dash. I recommend learning it that way, by the way. So A dash is equal to that, which is V U dash. So it's going to be 100 cos theta. I'm just putting some around that way. 1 plus cos theta. Plus U V dash. So it's going to be 100 sine. And the plus is going to change to a negative, and then there's going to be another sine theta at the end. So it's going to be equal to so 100. Let's take a factor of 100 out. Cos theta plus cos squared theta minus sine squared theta. Now, I don't like having sines and cosines squared thetas when there's not a plus with them. So I might change sine squared theta. So sine squared theta plus cos squared theta is equal to 1. So then sine squared theta is equal to 1 minus cos squared theta. So we get 100 cos theta plus cos squared theta minus 1 plus cos squared theta. This is looking good. And this is going to give us 100 lots of 2 cos squared theta plus cos theta minus 1 And factorizing this, so let's say... Now, advanced, you guys haven't done substitution. So, how the hell would you do this thing without using substitution? Factorizing this without substitution. Maybe you have. I can't remember. I know in advance you could do it with substitution. So basically, the point is that if you let, let's say like let's let t be equal to cos theta, and this becomes 100 2t squared plus t minus 1, and then you just factorize this, which gives you, so it's going to be t, I don't think this is right though, like I don't think this is how you guys do it, but that's okay. We'll just get through this one because I'm done. And then you substitute the t back into that once you're done, okay? I mean, you can do that without doing the t substitution, but cos theta plus 1 to cos theta minus 1. And so you're effectively looking for when these are equal to 0. So one is cos theta plus 1 equal to 0, and one is 2 cos theta minus 1 equal to 0. Cos theta is equal to -1, or cos theta is equal to a half. Now, since theta is acute, so come back up to here, have a look at our picture. It's an acute angle. Okay, so since it's acute, it has to be between 0 and pi on 2. So it has to be this solution here that we have to use. It can't be this solution on this side. So theta must be equal to pi on 3. So now to check to make sure that's a maximum. So for maximum, we're talking second derivative, and it's f. It's a double dash. And oh my god. Let's go back up to this thing. I don't want to do this. Let's just test point either side of it. That's another way to do it. So to test if it's a maximum point, you just test a point either side of it. So what's close to pi on 3? Pi on 3 is the same as... so pi on 3 is the same as... 4 pi on 12, so let's go 3 pi on 12 and 5 pi on 12. So... I want to substitute that into the first derivative. Okay, so it's going to be 100. Sorry about this one, guys. This one's a bit of a mess. Cos of, so let's say 5 pi on 12 plus 1 2 cos 5 pi on 12 minus 1. This will be really close. Okay, let me just test to make sure 4 pi on 12 is equal to 0, because if it's not, then me dumb. Me dumb. Wow, okay, so... Oh wait, no, I want a maximum, don't I? So this is approximately equal to So in a... No, I want to substitute it into the original. Of course. Oh, that makes it even easier. Okay, so it's going to be 100. So 100 sine. So the reason why I want it in the original is because I want to check either side of the original function, because if I know it's at the peak in the original, then either side it should be a little bit lower. So 4 pi on 12, close it off, then it's 1 plus cos, not that, 4 pi on 12, so it's equal to about 3.6. So if I change this to a 5, and if I change this to a 5, it gives me a minimum. I give up. I actually give up with this one. I don't know what. Yep, I don't know. I do not know. Stuff it. Let's ignore it. Move on. Okay, 33. Oh god, how many more of these do we have to go? Oh, it looked like we were so close before, and now it's so far. Okay, whatever. We might do 33, and then I think we'll have to call it there, because it's getting way too late for me. And then we'll finish it off tomorrow, I guess. Okay, so 33. Prove that 1 over 1 plus minus sine x plus 1 over 1 plus sine x is exactly equal to 2 sec squared x, where sine x is not equal to plus or minus 1. Well, that makes sense, because if sine x is equal to 1, then you get 1 minus 1, which is equal to 0. 0 doesn't work on the bottom, and same with the negative 1. So to do this, we can take left hand side and turn it to right hand side, I think. Yeah, I think that's what we're going to do. So to add the fractions, multiply the bottoms, and then cross multiply. So we get 1 plus sine x plus 1 minus sine x over 1 minus sine x, 1 plus sine x. Okay, the sine x's on top are going to cancel out. We're left with 2 over 1 minus 2. Oh, hang on. Yep, 2 sine x. Okay, do we just put it in that form? Well, it's just the difference of 2 squares, isn't it? That's not right. It's going to be 1 minus sine squared x. Okay, and then 1 minus sine squared x, so using that rule from before, where sine squared x plus cos squared x is equal to 1, means that, well, in this case it's going to be cos squared x is equal to 1 minus sine squared x, so wherever I see that I can substitute it with that. So it's going to be cos squared x there. And 2 over cos squared x is just equal to 2 sec squared x, which is what we want. Cool, okay, that was easy. Alright, last one, I hope. The region below shows below represents the area between the curves. This and this for the domain. Okay. Calculate the area between the two given curves in the given domain. Okay, well, this is nice and easy. So the reason we want part 1 is because we actually want the sum of the two. Oh, I see, because it's this area and this one here. So that's g of x on the bottom, that's f of x on the top, okay? And so this is the line that divides them up. So if I just did the integral of f of x, that would give me just this bit here. But if I did the integral of g of x, it would just give me this little bit here. So what I need to do is I need to add them together. So the integral of f of x plus g of x dx, and where's it from? It's from 0 to pi 3. Okay, is the equivalent of 0 to pi 3 Now f of x is 1 on 1 minus sine x, plus, and then gx is -1 on 1 plus sine x. And I think, no, it's a negative. Okay, I'm going to do it this way. Plus 0 to pi on 3 of gx dx. So 0 to pi on 3. So it's almost what we wanted, because we effectively want something that looks exactly like this so that we can turn it into that. That's pretty much what we want. Because if we can do that, it makes it so much easier. Actually, which means I would want it in that other form. So basically, undo all that stuff I just redid. Ugh. Okay, cool. So, looking at this right now, how does that relate back to what we had up here? So it's 1 plus 1. Well, because this is in the negative area, so this one's in the negative area, we have to take the absolute value of that, don't we? Because it's going to be a positive value, yeah. Because if you think about it, it has to be a positive area, and by putting, because we're finding the area between the curves, okay? The integral is -1 over 1 plus sine x, but we're looking for the area, so we're looking for that positive area, so we're going to have to do the absolute value of that area. And realistically, you should be doing the absolute value of any integral if you're finding the area anyway. So by doing that, that allows us to go to this, which gives us this, which gives us the integral of sec squared. So if you're not sure what the integral of sec squared is, it's on your formula sheet. The integral of sec squared, of course, is just tan x. And runs from 0 to pi on 3. So it's going to be equal to... it's 2 lots of this, isn't it? It's 2 lots of tan x. So it's 2 lots of tan pi on 3, which is just 3 minus 0. So it's equal to 2.3 like that. Okay, I'm calling it right there because I am absolutely buggered and it's 12:30 at night. So, we're going to finish this off either tomorrow or on Saturday. I'm leaning more towards tomorrow. But with that being said, I hope you guys have got something out of this. The second half of the exam is always a bit harder, just to keep it, that in mind, especially when we got to like this problem here, where I just gave up because honestly we did so much and just weren't getting answers that we wanted. So yeah, gross, yuck. Don't stay up all night doing maths. Like, don't do that to yourself. That's so silly. Get good night's sleeps, and yeah, especially before your exams as well. Don't stay up and study all night, because if you go in tired, you're pretty much working at like a lower remembrance capacity anyway. So anyway, that's pretty much it. So if you guys enjoyed the stream, make sure you subscribe to the channel, because that would really help me out. Getting close to 95 viewers, or subscribers I should say. So yeah, it's looking forward to it. So I don't know what I'm going to do for the 100, but we'll find something to do. Alright, with that being said, I hope you guys enjoyed the rest of your evening, and I will talk to you guys in an upcoming week. Ciao.
HSC.